Hi guys, in this video I'll go over the first half of the Alkyne chemistry handout. The first page here shows our reactions of alkynes, summary of all the reactions. As we go through this, we'll see that many of these reactions, most of them, particularly the ones at the top half here, are very similar to our alkene reactions. The difference is an alkyne has two pi bonds. And in a lot of cases we can thus do a reaction twice. For example, we know that an alkene will react with HX. We can do an addition of HX. But if we back that up, we can also do addition reactions with alkynes. They have two pi bonds. And so we can add one equivalent of HX. This will give such a product here. And then we can add a second equivalent, just as we've been doing for the past 2 or 3 weeks. So we have reaction with HX, such as HBr or HCl. We will also see reaction with elemental halogens, such as Br2 or Cl2. Of course, this is going to add in a trans manner, or anti-addition of the halogen. Mechanisms are going to be very similar to with alkenes. And then this alkene will react again with halogen to do another addition. So it's somewhat like twice the fun. One equivalent, then the second, one equivalent, and then the second. We'll also hydrate alkynes. Add water to the alkyne. We'll see that that gives an enol structure here. The enol is not stable. It will undergo a rearrangement called a tautomerization to place the double bond between the C and the O instead of between the C and the C. And of course the C double bond O is a carbonyl, and this precise carbonyl compound here is a ketone. So hydration of this alkyne actually gives a ketone rather than an alcohol. We can also hydrate using hydroboration oxidation. Of course, this is going to be an anti-Makarnikov addition. Very similar mechanism as we talked about with alkenes. Then this enol will undergo tautomerization to the carbonyl form. This just shows a couple of examples of the above. We will also see reduction of alkynes. This could be either by hydrogenation using H2. This would be a full hydrogenation or a double hydrogenation, and this will be a partial hydrogenation. Full hydrogenation goes all the way to the alkane. Partial hydrogenation goes to the alkene. And the alkene will be cis, because we know that the hydrogen comes in from the metal catalyst from the same side, so it's a syn addition. We'll also see this reaction here. This is called a dissolving metal reduction using sodium metal in liquid ammonia. This is a way to convert alkynes to trans alkenes as opposed to cis alkenes. Okay, so that first page is a summary of our reactions. This next page is just shows you some drugs that contain alkynes or alkenes. For example, the last three all contain an alkyne. Ethinyl estradiol, a contraceptive medication. Tazarac, an anti-acne medication, contains an alkyne. And also Lamisil, an antifungal compound, contains an alkyne as well as an alkene. And then this fused, these two aromatic rings fused together. So some examples of compounds containing an alkyne. Before we look at the chemistry, let's look at nomenclature of alkynes. Very similar to all nomenclature, longest continuous chain. First though, let's look at the idea of terminal versus internal alkynes. A terminal alkyne, the alkyne is at the end of the chain. Thus, the last carbon is bonded to an H. In an internal alkyne, the alkyne is not at the end of the chain, and thus the alkyne carbons are not bonded to an H. So that's a little terminology there. Two different types of alkynes in general. Okay, nomenclature, longest continuous chain. Of course, just as with alkenes, the longest continuous chain must contain the functional group of the alkyne. So we might as well start here. This is 1, 2. Keep in mind that this is linear because each carbon is sp linear. So don't lose track of your carbons. 1, 2, 3, 4, 5. 5 carbons. There's no branching here or anything. And so this would be pent. But we have the YNE ending. Pentyne. But just like with alkenes, we note where the alkyne is. It's between the 1 and 2 carbon. We just note the first position, so this is 1 pentyne. Now alkynes are never stereogenic. Because it's linear here, there's no cis and trans possibility as with alkenes. Okay, let's name this compound here. You should maybe do this on your own before continuing on with the video. Longest continuous chain, 1, 2, 3, 4, 5, 6, 7. Either way you go, 1, 2, 3, 4, 5, 6, 7. So that would be a heptyne. And the alkyne is at the 1, 2, 3, 4. But if we started over here, it would be 1, 2, 3. 3 heptyne. There's actually no such thing as 4 heptyne. Okay, the original compound as shown is 3 heptyne. What if we added a chlorine here and gave it some stereochemistry? What would that compound be? That would be, well, still heptyne. The one end would still be here because the functional group takes precedence. Still a 3 heptyne, 3, 4, 5, 6. That would be 6 chloro, three heptyne. But we have stereochemistry here. That's a chiral carbon, and we have some precise stereochemistry shown. Chlorine is 1. Carbon with another carbon would be 2. Carbon with no other carbons would be 3. H is in the back. Clockwise, we can call this R. Six chloro, 3 heptyne. Okay. So your nomenclature is pretty straightforward, as very similar to nomenclature of alkanes and alkenes. Okay, let's look at reactions. First, we're going to react with HX. And we're going to do addition reactions. We can add HCl to the alkyne. give an alkene, we can actually add a second equivalent of HCl to the alkene. And now we're going to have two chlorines. We'll see that the chlorines are going to be on the same carbon, and thus this is called a geminal dihalide. Geminal meaning twins. They're on the same carbon here. Okay, mechanism for this addition. H plus, Cl minus. Pi bond will attack H plus. Just as with alkenes, where we're going to leave cation, right or left? Well, the answer would be left. So the electrons pull away from there, attack the H plus, and we get boom, boom, boom. I'm going to go ahead and draw this like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. New H. I'll draw in the existing H, or the original H. 1 pi bond reacted. We're left with a pi bond still there. And we now have a plus charge here. The electrons just swung out, made a new bond to H. Either one of these we can consider the new bond. I'll consider it that one. And so the pi bond swung out to make bond to H, leaving that as a carbocation. And that would be a secondary. Now, this carbocation is a little bit odd in that it's on an alkene carbon, because we have 1 pi bond left. Now, sort of a slang name for an alkene carbon is, or an alkene, is vinyl. So this is known as a vinyl cation. Now, a vinyl cation is actually pretty bad. It's actually worse than like a primary or a CH3 carbocation, because the hybridization is sp. There's only 2 electron regions, and actually it's linear there. It's still linear. I drew it sort of bent because that's where we're going to end up once it becomes sp2, but it's actually linear here, sp. 50% S character, where our typical carbocations would be sp2, less S character. Now, more S character stabilizes a negative. It actually destabilizes a positive. Because the empty orbital is closer to the nucleus. That's not a good thing. It's basically your positive charge is closer to the nucleus, if you want to look at it that way, and you got a plus closer to the positive nucleus. We could discuss that more, but in the end, that's a pretty unstable cation, and actually some chemists prefer not to show vinyl cations. Now, some books discuss these in detail or more in depth. I'm not going to do it. We're going to show them, and we're going to proceed from here. Now, we can't say that this is not formed because there's no back bonding possible. The H doesn't have a lone pair. So this is an actual intermediate here. From here, that's that. Now the chloride can make a bond there, and when it does, well, there's your product, or your first product. We did an addition of HCl to the alkyne. It gives this product here. Now this is an alkene. Alkenes can react again with HCl. We've been reacting alkenes with HCl for a good 2 weeks now. And it can continue and react again with a second equivalent. We have H plus, Cl minus. Where we're going to leave cation, left or right? The answer would be left. So the electrons pull away here. And we get boom, 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 boom. New H here. Positive here. secondary cation. That would be better than making a primary cation. But here there's another reason for why this is the best cation. And the answer is resonance. We can draw a resonance structure here. These electrons can move in here. It almost looks like back bonding. But this electron movement gives boom, 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 boom. Gives this structure. And these are resonance structures. All we did here is move pi electrons. One of these lone pairs is in a p orbital. Why? Because there's an empty p orbital next door. It doesn't have to be empty. There's a p orbital next door. And so one of these lone pairs is going to want to be in a p orbital. As soon as this cation is made, you have overlap between lone pair and p orbital. It's there. This structure does not adequately show that. This structure, which we drew on our paper, shows that p orbital overlap more clearly. Now, whenever we have resonance, the true structure is somewhere in between. And this is the old story, it's like colors. I'm showing red and white, but I'm asking you to understand that the true color is somewhere in between, which would be pink. Now, the structure in between is going to have sort of partial bonds, and it's called the resonance hybrid. As we progress and talk more about resonance during test 3, we will talk more about resonance hybrids and other things associated with resonance. Importantly, resonance is a stabilizing effect. One thing it does, it delocalizes the charge. The blended true structure here has only partial positive on carbon. The other bit of positive charge is delocalized to the chlorine, as we see in the structure here. So charge is delocalized. That's a stabilizing effect. That is the major reason here of why the cation is formed on this carbon and not that carbon. We will see resonance again on the next page when we look at tautomerization. Okay, resonance is here. How do we get the final product? Well, the Cl- that's up here attacks cation. That gives final product. We now have 2 chlorines bonded to that carbon. Now this arrow is our resonance mechanism arrow. We're showing the resonance. Okay, one thing we can talk about or state about resonance structures is you can always work with either one. Or maybe there's multiple. Maybe there's 3 or 4 resonance structures. You can always work with any of them. Actually, none of them are strictly correct. For example, we could have added the Cl- to this structure, and we could have added it here and moved these electrons back up. That arrow movement would also give that product. You can always work with any of your resonance structures. Okay. So, ultimately we added 2 equivalents of HCl to an alkyne, and this will produce a geminal dihalide because the second cation is formed on the same carbon that the first halide sits on, mainly because of resonance. There is a neutral intermediate here. It would be the chlorinated alkene. It is possible to obtain this product with just one equivalent, but if you react this with two equivalents, you're going to go all the way to the geminal dihalide. Why is a vicinal dihalide not formed? Well, we explained that. A vicinal dihalide would have the two halogens on adjacent carbons. That is, the second chlorine would be here. Then the two chlorines would not be geminal, but they would be called vicinal. They would be in the same vicinity, but not on the same carbon. Well, the reason we don't get a vicinal is because the second cation is not formed out there. It's formed here. And thus the second chloride attacks here. So, ultimately, it's addition of HCl, but it's twice the fun. But hopefully, again, you see the consistencies with our alkene reactions. Okay. Reaction of alkynes with elemental halogen. One equivalent gives a alkene with the two halogens. These would be vicinal, but that's an alkene, and we can react again with elemental halogen, add halogen across the pi bond, and now we would have two halogens on each carbon, and this would be a tetrahalide. Okay, mechanism pretty consistent. We got Br2, schizophrenic. Where we're going to leave cation, right or left? The answer would be left, so we attack bromine. These electrons off. Of course, elemental halogen is not ionic like HCl, but it still can be electrophilic. This is going to give boom, boom, boom. 1, 2, 3, 4, 1, 2, 3, 4, 5. Here. There's an original H, we added a Br, and cation here. Now I'm going to be consistent with our previous reactions. Some textbooks may do this a little bit differently, even with alkynes. I'm going to say that this is going to back bond here. And I'm going to say NAF, and we're going to get to, I'm going to draw this like this. Boom, boom, boom. Back bonded. The bromine is now positive. Looks like a bromonium ion. That's a little ugly. This carbon is sp2, ideal bond angle being 120 degrees. Right now we have a bond angle here of 60 degrees. That is a lot of strain. Some books will discuss different mechanism here. I'm going to do it this way. Again, because this is consistent with our alkene reactions. At this point, first off, we made this plus Br minus right here. Br minus is formed. Now these electrons can come in here. We're going to attack here, yeah? Remember, we attack here because we attack the same place there would be a cation. This thing is going to pull. It can pull more here and leave more partial plus there. It's the same discussion we had with alkenes. Alkene addition reactions. There, move these electrons back to the bromine, and that will give that product right there. And we see that the two bromines are going to be trans, or it's an anti-addition. Of course they will be, from our standard mechanism. And the bromines are high priority and they're opposite, so that's E. We do not expect Z here. The mechanism shows us that we're going to get E and only E. Okay. At this point we have an alkene. Alkenes react with bromine very easily. Add a bromine to each carbon. That'll give us this product. Now you can go through the mechanism. It's the same mechanism we have done before. You did that reaction. You brominated an alkene in lab. Bromonium ion, backside attack. The thing to recognize is this product has absolutely no stereochemistry. There are no chiral carbons here because each carbon has two bromines. No stereochemistry here to consider. So we can draw these bonds any way you want. Yes, that's tetrahedral. Yes, two in the plane, one forward, one back. But it does not matter. The carbons are not chiral. As long as you have everything connected, the projections do not matter. Over here it did. Because if we had drawn this bromine up, then both of them would have been on the same side and that would have been cis or Z. But we know that this first step does not give Z. Okay. Ultimately, we can add two equivalents of bromine to an alkyne, and ultimately we can make a tetrahalide. All right. Now, the remainder of this handout was covered in the second video. That will also be posted. So at this point, because of the cancellation of class, I'm covering this the first half of this handout by video. So again, the review sheet, what I went over in this video was the nomenclature, and we went over this here, yeah? So this was video 1. And then the hydration involving formation of enols and then tautomerization was video 2. As well as reduction. Reduction of alkynes included hydrogenation, either with regular catalyst or a poison catalyst. The poison catalyst gives cis alkenes. Trans alkenes can be made using the dissolving metal reduction of sodium metal in liquid ammonia. And so that was video 2. Video 1 is because of this would have been our Wednesday lecture. But this is apparently going to be canceled because of the impending hurricane. Video 2 would be the following Monday lecture. And this video I'm having to do because I will be out of town on Monday and I will not be able to hold class. Instead, I'm covering the Monday lecture material by video only. And that's the second video in this series, and that covers the remainder of the Alkyne handout here. The following Wednesday of next week, we will regroup. I will also send an email about this. Okay, guys. See you soon.